Okay, let's have a look at a continuous random variable that is distributed as a binomial, but let's try approximating a probability using the normal distribution. So how about we let the probability of success be 0.3, and let's do n trials, n Bernoulli trials for our binomial. So I'm saying we've got this binomial where it's 25, 0.3. And let's try and find the probability that the random variable turns out to be bigger than or equal to 9, let's say. So we're going to not, because there's 25 different trials, to work that out precisely by hand is going to be quite a big effort. I'll explain what I mean. This is a binomial, so we've got success is 0.3, failure is 0.7, and it's to the power of 25. When you go along and you 25 see 0, 0.3 to the 0, 0.7 to the 25, plus 25 see 1, 0.3 to the 1, 0.7 to the 24, plus You know how many there are of those? 26, right? All the way along to the last one, 25 see 25, 0.3 to the 25 and 0.7 to the 0. There's 25 of those, 26 of those. Now we want the probability that it's bigger than or equal to 9. So we want from 9 up to 25. So I'm going to be taking 9 off those 26. 17 of them that I'm going to have to work out and add together to get that answer. 17 individual ones of those probabilities. I don't want to do that. So I might see if I can use some other way to at least estimate the probabilities. And the way that we're thinking is we might use the normal distribution. Now, there's a little quick rule of thumb that if NP is bigger than 5 and NQ is bigger than 5, then we're looking at least having some sort of chance of success in this process. So, P is 0.3, N is 25. So 25 times 0.3. So we need to work out what that is. 7.5. Yes, it's bigger than 5. So that's a good start. The next one, if that's bigger than it, that's 0.3, then 25 times 0.7 is clearly bigger than it as well, but it equals to 17.5. So clearly that's true. If both of those are true, then we're on good track to be able to use the normal approximation for the binomial distribution. So my first step would be to check that. And in checking it, I've done something good here because I've found NP is the expected value of a binomial distribution. So I've already calculated the expected value. So let me get rid of this up here now and write down what I'm going to keep. The expected value, or the mean, is NP for a binomial distribution, which is 7.5. Otherwise, we can get rid of that now that we know we can use it. Another thing I'm going to need is the variance. Well, I'd like the standard deviation if I'm working in the normal distribution, but I'm going to work out the variance. And we know the variance is NPQ. So what is 25 times 0.3 times 0.7? 25 times 0.3 times 0.7 is 5.25. So our variance is 5.25. So if I'm going to approximate this binomial distribution with a normal distribution, I'm going to now be looking at a normal distribution, x being part of a normal distribution, where it's got a mean of 7.5 and a variance of 5.25. Remember, that's the variance, so I need to square root that if I'm going to be using z-scores and things like that, calculations. All right, so now I can get rid of this stuff because I've used it to figure out which normal distribution is going to slot on top of my binomial distribution and approximate it. Now the trick. There's 25 discrete possibilities here for this random variable. You're going to have no successes, 1 success, 2 success, 3 success, all the way up to 25 successes. Sorry, there's 26 different possibilities. And those 26 possibilities each have a column if you draw them as the discrete random variable versus the probabilities. I'm not going to spend the time drawing them all, but 0, 1, 2, ... We're going to be up at 9, 10, right? Here I'll go 8, 9, 10, and ... right? And if you draw all these up, you're going to get little columns that are your probabilities. You know, there's 8, there's 9, there's 10, let's say, roughly. And each one of these has a probability associated, which you can calculate by expanding out that binomial expansion that we did before. Each of these columns has a certain thickness, and it is relevant because the number's still quite small at 25 trials. So the column's thickness does still make a bit of a difference to the situation. Now, if I go and I plonk a binomial distribution on top of this, so let's say, I'm imagining actually we're past there, so we're probably coming down when we get to here, let's say. We're about there. So our binomial was heading up, right? And then I'm ... But I've ended up at the top and I'm coming down and heading ... right? Back out there somewhere. So I've got some sort of binomial curve. It's just, I haven't drawn the whole thing, but it goes up and down like that, but this is missing, right? I've just drawn a part of it. But the part of it that I've drawn, I'm very interested in, because if I want to know the probability that the binomially distributed random variable is bigger than or equal to 9, if I just go to 9 on here and find this area out to the end, I'm actually missing a part of the column, and that's a big area there, that represents actual 9, because it's a discrete random variable. 9's not just some value out of an infinite number of possibilities on a continuous random variable. So what I want to do, if I want to include, not just be bigger than 9, but also include 9, then I'm actually needing to include 9. I'm actually needing to come back here and include all this bit of the area as well as the bit from 9 onwards. I'm wanting to include that bit as well. That's going to give me a better idea of what we're talking about. It's got all of 9 included, plus everything that's bigger than it. But that means, in terms of approximating it with the normal, I need to go here to 8.5. All right, so we come up here at 8.5 to the normal, and we're going to be looking at this area under this normal curve to approximate the green stuff, which is, I should have been out there, which is that stuff there. All right, so I need to go from 8.5, and we discussed this on another time where if you need to include the column, you've got to be careful. And if you're going something bigger than or equal to, then you need to jump back by 0.5 so you can include the whole column. So I'm actually trying to find in the normal distribution that I've got the probability that x is bigger than or equal to 8.5. And that's known as a continuity correction. Now we can go ahead and do it. All we need to do is take this normal distribution that I have written down here and map it back to the standard normal distribution, because we can use tables or a calculator to find out the area required, which is the probability. So we're going to map it back to the standard normal distribution using that z-score. That's what we wanted to do. So the z-score that we're after, we know that you put your actual score, you take off your mean, and you divide by your standard deviation. So we're going to put in our 8.5, we're going to take off our mean of 7.5, and we're going to divide by our standard deviation. 5.25 was the variance. So you'll notice that with most normal distributions, they'll give you the mean and the variance, although if you're looking at something about sample proportions, p hat, they'll often put the standard deviation as the second number there. But anyway, this one has the variance there, so I need to square root that variance of 5.25, and I get 2.29, 2.2913. So if I map 8.5 back to what its value would be if it was on the standard normal distribution, its value would be 0.4364. Okay, so what we're saying is we've now mapped back to our standard normal distribution, which looks something like this. There's 0, there's 1, 2, 3, minus 1, minus 2, minus 3. And we've decided that 0.43, which is about here, this 4364, this is where the value of 8.5 maps back onto the standard normal distribution. Now, depends what table you get as to how you're going to find your answer. We want to know the probability of being bigger than or equal to this, which is just that area there. We want to know that area. But if you only have a positive table of values, if you find the area associated with 0.4364, it's actually going to give you the area up to there, from minus infinity to that. So if that's what you find, you need to subtract that away from 1, so you can find the actual answer. If you had a full set of tables, you could use symmetry and just find the area up to minus 4.34. If you find on the table minus 4.4364, it'll straight give you the answer. So I'm going to assume that they've given you just a positive set of tables, first of all, and I'm going to go to 0.43 and 0.436. It's about 0.44, so it's 0.67003. I get for this area up here, this area in here is 0.67003. That means my answer is going to be 1 minus that, so I can find the actual area I want. So 1 minus 0.67003, 1 minus 0.67003 is 0.32997. that is about a 33% chance. About a 33% chance, or they need to know the probability that x is bigger than or equal to 9, probably about 0.33. It saves me adding 17 different individual probabilities together from the binomial expansion. What should have happened is if I went to negative 0.4364, so negative 0.44, I went straight to, and it says 0.32997. It goes straight to the answer. Now you can use your calculator to work this out as well. If you have one of these calculators or a Casio 100, you can go Shift and 1, and you need to type in distribution. So you need, on this one it's 5 for distribution. P gives you the area from minus infinity up to the number you put in. Q gives you an area between two values. And R gives you the area from the number you put in upwards, which is what we want. So I need to put 0.4364 in there. For R, I need to pick 3 and put 0.4364, which is more accurate than what I was able to do on the table because I had to round that to 0.44. And that gives me 0.33127. But like I said, I rounded it. Whichever way, I get about 33% or 0.33. So I've used the normal distribution to approximate this binomial, but the normal distribution is a continuous random variable. The binomial is a discrete random variable. I need to have a big enough number of Bernoulli trials to make it even a possible thing, but it is an approximation. But I'd rather do that than add up 17 separate probabilities in an expansion of a binomial.